This is decision 2 from 2023. Let's just do it. So we've got a feasible flow given by these numbers in the circles, and then the other numbers are the maximum things on each arc. Set the value of the feasible flow where you've got 20 plus 15 plus 19 coming out here, or alternatively, you've got 10 plus 44 coming into here. Either way, the answer is 54 for this feasible flow. The capacity of C1, so just be careful here. The capacity is the maximum numbers you're looking for, so not the circle numbers this time, but the maximum on each arc as you go through. However, if an arc actually leaves the cut, so this, notice BC, is not going into the cut, it's coming from inside of it to outside of it, because the cut, you can imagine the inside of the cut being this side, the right side of the cut. BC is going outside of it. It starts inside, going outside, so we don't have that 17, so it's going to be 17 plus 8 plus 5, plus 17 from this bit here. Ignore that, and then we plus the 11 plus the 18, and we end up with 71, and likewise C2, this is going into it, this is going into it, so that's good. This is also going out of it here, is it not? If we imagine this being the inside, the right of the cut, this is going to the outside, so don't include that. But do include that one, and that one, and that one. And we end up, are we not including this one? It's going to this side of it. Why would we not include the 6? Oh, we have done. I just added it from the top downwards instead of the bottom upwards. Fine, cool, whatever. We get this answer anyway. And then it says, by inspection, find a flow augmenting route to increase this. So what we could try is just, well, let's increase this by a couple because we can. Says by 2 units. So we can increase this by a couple. We can increase this by a couple. We can't increase this. So we're going to have to go this to this. Then from F, we can't increase over either of these. However, we can decrease this one by 2. We can make no flow go from here to here, which means we need extra flow to come out of D. But that's fine because extra flow can come out of D. So just because this arrow is going the wrong way doesn't mean that you can't do anything with it. It just means that to make progress from F, we decrease rather than increase to get ourselves to D. So increase by 2, decrease by 2, increase by 2, increase by 2, and we should end up with a route that would work. And then prove once the thing is applied, the flow is now maximal. Now, to do a proof in these kind of questions, you're basically just thinking about the flow cut theorem, the maximum flow minimal cut theorem. That's basically what we're thinking. So you look in this picture as hard as you can until you find the thing that allows you to find a cut of 56, because we've just done a flow of 56, 54 plus 2. So we look in here as hard as we can for a cut of 56, and then we just write down the theorem. And here the cut is eventually, you find it. It might take a little while, but just sit there trying to, you've got a calculator, just try stuff as much as you can. Eventually you'll be in there and you'll find it. So this is a decision tree then. So we just start with a rectangle, then circles, then triangles. And the choice is whether to insure or not to insure. So that's the first bit. And then the probability bit is rain or not rain. So that all goes in there. And then we just need to read carefully what the numbers say. So if it doesn't rain and we're insured, then we will clearly make 15,000 for it not raining. However, we have paid 2,000 for insurance. That's 13,000. The next one maybe is if it doesn't rain and we're not insured, we'll just make 15,000, obviously, which is great. It's the most we can make. However, if it rains, we will be losing this 20,000. If we're insured, we'll get 16,000 back, but we are still paying 2,000. So that's a 14,000 difference. With the 20,000 we're still losing. That's going to be a 6,000 loss. And if we're not insured, it's just straight up to 20,000 loss. And now we just work out the numbers inside these two circles by doing this times this plus this times this. Gives us this one. And likewise, this times this plus this times this gives us this one here. And we find that the larger value comes with insurance, so we will be taking that value and we will be insuring, since that gets us a higher predicted value. Question 3 then, so this is a costing table, so this is how much it costs to transport from like A to Q, and then this is saying A can supply at most 45 things, and Q needs at least 75 things. All it's asking you to do to write as inequalities is just to say, well, the things coming out of A need to add up to no more than 45, because that's the maximum A can supply. So the things from A to any of the other places, QRS, need to add up to make most 45. It's as much as A can supply. And likewise for B, C, and D, just with their relevant numbers. And then likewise for Q, R, and S, they need at least 75, 37, and 44 of things. So the inequality is going to flip over, and the sum will put the Q second because we're adding that it works in terms of IJ, right? So this is the suppliers and this is the destinations. So Q needs to, from the four suppliers, A, B, C, or D, the sum of things going to Q needs to be at least 75. So that's what we're just writing here. And we just write them all down and we end up with our 2 marks. Northwest corner then, so we start putting as much as we can in here. Of course, A can supply at most 45, so we'll put 45 here. Q needs 75 things, so we'll fill up column Q until we reach 75. So B can supply 27 things. We're still not at 75 yet. We're only at 72, so we give 3 more things from C. C can now supply another 31 things. Now we move across to R and give it 31 things. It needs another 6 things, so we give those 6 from D, and then we finish off the table. We're going right there. So we fill up the columns before moving across a row when we do that method there. And now it says taking AS as an entering cell. So we put a theta in AS. Of course, we need to make all the rows and the columns balanced when we do this. So this is going to need to be 45 minus theta. 27 can't be shifted. We need to make this row balance, but we can't put the theta away from the 27 because then there'll be nothing to balance row B. So we need to keep the 27 there and adjust with this 3, because we can take theta away from this 31 and balance this row as well. And now, of course, we need to put a plus theta in here and a minus theta in there to balance both this column and this row. So this will be it. We want to make theta as big as we can. None of these are allowed to be negative, so if we make theta 31, that one will become 0, and making them 31, if I just go backwards, like making them all 31 turns them all into this. So that will be our first thing. So there's our improved solution. Now it says make an actual one further iteration. So what we're going to do is I'm going to write out the costings table out one more time. I put a 0 here and therefore a 23 here. I'm just doing that algorithm where you just make the entries add up to their row and their column number at the top, starting with a 0 there. So 0, 23 needs to be there because 23 plus 0 is this. 23 plus minus 15 is 8. And 23 plus, let's say, minus 20, what is it? Not even sure, minus 12 is 11. You do a 12 over here because these need to add up, which makes a minus 1 there, and then it is a minus 12 over there. And now we need to fill in the ones that we're not using. So I only filled in the costings of the routes that I was using. I should have said that before. But here, the costings of the routes that are actually being used so far are in here. Now, to get the other ones, the improvement indices, I think they're called, we're going to do the missing value from here. So 18, for example, for this one, 18 minus 16 minus 0 is 2. 10 minus 16 minus 15. 14 minus 16 minus 12, and so on for all of those. Now, if any of those are negative, that is your new entering cell. So the reds are the improvement indices. These are the shadow costs. So we've done all that. The entering cell needs to be DQ. We'll call that theta. We'll balance this out using a bunch of thetas. So, for example, neither of these can be a minus theta because then there's nothing to balance their respective rows with. So that's going to have to be the minus theta. That's going to have to be a plus theta. That's going to have to be a minus theta. And then everything else just stays the same. The biggest we can make theta here is 13, which gives us this solution, just making theta 13 everywhere. And yeah, that will be it. Entering cell DQ. Exiting cell was the one that went away, which was this one here, DS. So yeah, good. That's that question done as well. And then the Hungarian algorithm question. So to start with, this is a maximizing question. Hungarian algorithm minimizes stuff. So in effect, we're essentially just going to turn all of these numbers over as our first step. To do that, we're going to find the biggest number in here, which is 52, and replace every entry with just 52 minus the entry. So this is 52 minus 34, 52 minus 20, 52 minus 18, 52 minus 15. And what that essentially does is it makes all the numbers that were biggest smallest, and all the numbers that were smallest biggest. So if we now minimize this new table, we end up maximizing this one here. So let's now go on with the Hungarian algorithm. It says rows first, I think. So yeah, rows first. So find the smallest number in array, that's 18. Take away 18 from every number, we get this. Take away 3 from every number, this. Take away 4 from every number, take away 0 from every number. Then we do columns, so take away 0 from every number, it's not going to do anything. I should have animated these as columns, shouldn't I? That's my bad. But anyway, so the first column, take away 0 from everything here. Here we take away 7 from everything, which gives us this. Here we take away 10 from everything, which gives us that. And here we take away 10 from everything again, which gives us this here. Good. And then, of course, we say, well, okay, we can cover up all the zeros with just 2 lines. If it's optimal, we would need 4 lines to cover a 4x4 table. So this isn't optimal. So let's find the smallest number of the non-covered numbers. That's going to be a 5. and take 5 away from everything, except add in 5 to anything that's double covered, which is just this 0 here. So that looks like that. So that's going to be every number in here taking away from 5, and then these numbers stay the same because they're only covered once. The number covered twice goes up by 5. Can we cover the zeros in less than 4 lines? Yep, you can do it like this pretty easily. So once again, take away the smallest number you can see from this block from every number in the block. So that's take away 1 from all of these, but then add in 1 to there and add in 1 to there since they're double covered, and then don't change any of the others. And you end up with this. And now it takes us 4 lines to cover everything, because you can try in your head if you want, but it's 1, 2, and then maybe 3 and 4. You can only do it with 4. So what we're going to say then is that we just need to allocate A, B, C, and D to the right things, finding the zeros. So for example, if we can't make A job number 1, because then C couldn't do anything, so A has to be job number 3, and C has to be job number 1. If job number 1 is gone, then B has to be job number 4, and then D has to be 2, because that's the only one that you haven't got yet. And we use the initial table up here to find the score. So it's A times 3, so it's, sorry, A doing job 3 is 18, and then B for 4 is 34, so it's this, plus, and so on, and you end up with 145. It's estimated only because the scores are actually estimated in the first place, not because there's anything estimating about this. But yeah, good. So now we're making a substitution here, which is fun. So first thing, I just doubled all this and moved the stuff over to make this. Now I'm going to make a substitution. So here, un plus 2 is just vn plus 2 plus 2 brackets n plus 2. So I'm just going to shove that result in there, and likewise shove this in there, and then this is just what they gave me. All I've done there that's intelligent really is replace this with an n plus 2, just because I replaced those with n plus 2s as well. Expand everything out, and what's nice about this is the numbers go away and you end up with this, which is great because you can look at the auxiliary quadratic to solve this, which is that. Solve this in a calculator, remember you get these two things, and so your answers are Vn, remember we're solving for V here, Vn equals A, one of these to the n, plus B, one of the other ones to the n, so it ends up being this. Of course, this is just 1 anyway, so that's fine. So that's good, but before I do that, I'm just going to say, let's go back a step. Vn is un minus 2n, and then just add 2n to both sides, and you end up with this. And now we can say this is just 1, so this is just a plus B maybe, and we end up there. Now we can actually find A and B by using these conditions here. When n is 0, let's just put a 0 in here. That makes u 0, 15, and that makes a 0, that makes a 0. So we just end up with this. And then when when n is 1, you end up with this, which simplifies to that if you double everything and move this thing over. Add these together and divide by 3 to find B, and then solve for A, and then put it back in the original thing. You get this. And describe the long-term behavior. As n goes to infinity, minus a half to the power a really, really big number is just 0, or basically 0. It limits to 0. So un, as n gets very large, just limits to a linear function, 17 plus 2n. It's very tempting to say just un becomes very large, but they want you to say it tends to a linear function of the form 17 plus 2n, that kind of thing. That's what they want you to say. So the dynamic programming question then, so apologies for this being very small, but we do need to read all of it as we go along. So she can visit these places in week 1, 2, 3, and 4. We're going to start at the end, obviously. So we start with stage 4, and she can only go to H, I, or J. So that's the state. The action is she does have to go home at the end. So the action is she's going to go from H to S, or from I to S, or from J to S, where home is described as S. And of course, the destination is S every time. This column is a bit pointless, but whatever. Now, the value of doing that, so we're saying here, she's giving a talk at H, which earns her 47, and then she's traveling from H to S. H to S is going to be a journey cost of 7 there. So it'll be 47 minus 7. Likewise for I, she earns 49 speaking there, but then she travels 8 to get back to S, so that's 49 minus 8. And then likewise for J, same kind of idea. And now we may as well just star all of those because you're supposed to put stars on the best outcomes. And technically that's the best outcome for this. It's the only one, but sure. And now we go back to stage step 3, right? Now in stage 3, she can either speak at F or G. Now, if she speaks at F, she can then go on to H, I, or J. So the action is speak at F and then go to H, or speak at F, then go to I, or speak at F, then go to J. Destination, of course, just H, I, and J, as I just said. Now, how much is that value? Well, speaking at F is 44. And then for this one, she'll earn 44. Then she'll travel to H. F to H is 6. and then she'll earn the amount that she earned at H, which was 40 in total, like the final amount she gets for being in state H at 4. So that'll earn her 78 in total if she does that. For I, likewise, she still earns 44 speaking at F. F to I is 7. And then from I, the best route is 41. So that's 78 as well. And then likewise for J, the same sort of thing. We'll start both of these just because they're equal, but that's okay. And now we'll say, well, also at 3, she could have done G. And likewise, it's going to be just GH, GI, GJ for the same reason, HIJ again. And then for G, she earns 45 for speaking at G. Traveling to H from G costs her 7, and then from H, she can earn 40. So you put those things together. And then likewise for the next one, 45 speaking at G, traveling costs 8 this time, and then 41 is what you earn if you're I in this state. And likewise the next one. And we'll pick the best, which is this one here. Now, things get slightly more interesting when we get to the next state, which is state 2. She can speak at C, D, or E. So we'll start with C. From C, she can go to F or G. So those are our 2 states there. Speaking at C, you earn 48, but you want to go to F, which costs you 7. And then from F, the best thing you can do is earn 78 from there. So that gives you this total. And likewise here, still 48. Going to G costs you 5, so we take away 5. And then once you're at G, the best you can earn is 79. So that's that there. So we have this star here. And so that will be the one we'll choose from now on in the future when we get to stage 1. Likewise, you can be at D, so this is the same kind of thing. All the numbers are the same. We star both of them technically because they're the same. Don't lose a mark just because you can't bother to star stuff. If it's the same, just star both. And likewise for E, same kind of business here. We end up starring this one. And then when we get to state 1, this is A or B only, but we can go to C, D, or E on the next stage. And then this is just going to be about picking the one that we put a star next to. So A earns, let's say, here it is, 47. If we're traveling to C, that costs us 3, but then we choose the best from C, which is 1, 2, 2. We put that in. We get this, do the same for the next one, star this one, and we keep going. The thing becomes very repetitive, and we keep starring the thing that's the best. And then at the end, we do have to go all the way home again. So we'll put maybe state 0 here, and S, because we are going home. From S, you can only go to A or B. So now we just have to pick which one was better along with the minus of how much it costs to get to A or B. So this first one will just be -5 plus the total we get if we choose A to be our first route. And then, of course, -2 plus the total we choose if we choose B. And we end up with this. So the best route is starting at S, obviously, going to A. We got the 161 from going to C. We then got the 122 from going to G, which then went to J, which then obviously went home again. And the total is 161, but that's in hundreds of pounds, so 161,000. Good. By the way, if you make a numerical mistake, you risk losing an awful lot of marks on that question. So just do it very slowly, very carefully. Do not misread a number in the table, and just it's 13 marks. Make it take 20 minutes, like you've got the time. Question 7. Decides to open a bank account, sure. So first order recurrence relation, well, it's just UN equals whatever you add in, which is K. And then she spends a quarter of what was in the account before. So she's still got 3/4 of what was in the account. So it's just 3/4 of what was in the account before, UN -1, and then just plus the amount that's added every time K. Now, we can solve this as sort of as if it was a second order linear equation where we can just say, well, it's just M minus 3/4 equals 0, and just ignore this for a second. Solve that for M equals 3/4, which means this is the first bit of the solution. It's just like the auxiliary quadratic, but it's not a quadratic because it's only a linear term. And then we can just say, well, to get the rest of it, we just set UN equals some lambda, which means UN -1 is also lambda. So we get lambda minus 3/4 lambda equals K, which gives us lambda is 4K, and then we just add that on to the end. So I essentially just did it like it was a 2-dimensional equation, except there was no quadratic anywhere. So yeah, kind of nice and straightforward. And yeah, can we solve for A, I guess? Well, we know that there was K at the end of the first month, so when N is 1, we end up with K in the account. And we can rearrange this for A, we get this, and so it ends up being that there. At the end of the 8th month, we need at least this amount. So when N is 8, we want to be bigger than or equal to, I guess, this here. We can actually be a bit more intelligent here and just factorize out 4K maybe. This is a positive number because this here is less than 1. So we're happy to just divide by whatever this is without messing with that sign. And then we can divide by 4. Technically, we need to be bigger than this if we're rounding to two decimal places, so it's going to be 486.18, I think will be the answer that we need in pounds. And the last question then, there's no stable solution. You're looking for a saddle point for there to be a stable solution, which is equivalent to saying that the row maximum needs to equal the column minimax. So the maximum of the smallest of each row, so the smallest of this row is -3, then -1, then -1, then -4. The maximum of those is -1. And the column minimax, so the smallest of the biggest. So the biggest one here is 4, the biggest one here is 2, and the biggest one here is also 5. So the minimum of the biggest is this 2 here. Those two aren't the same, so there's no saddle point, and therefore there's no stable solution. Explain why A should never play option T. It's just dominated by option Q, right? They get less if the opponent plays X, less if the opponent plays Y, and less if the opponent plays Z. And you needed to write those comparisons in for the second mark. So yeah, we'll maybe cross out T, since whenever they ask you that question, it basically means don't consider that row again for the rest of the question. Player A intends to make a random choice between Q, R, and S with probability these, and wants to use a simplex algorithm. So okay, let's set this all up then. So by the way, this is the table that they give you, and this is quite helpful for knowing exactly how many extra things you need to add in, because you can count the rows and or the columns and the rows to know how many basic variables and stuff you need. So I'm going to need to add in 4 slacks because of the 4 things that are here. So okay, firstly, I need to make all of these positive. So I'm just going to add 3 to everything to get this, or 0, positive or 0. So adding 3 to everything is going to be enough. You could add 4 to everything to make everything strictly positive, but it's enough to just do this. And now we can set up that V, we're going to call V the amount that they win, I guess. And V is equal to, if the opponent plays X, is 0p1 plus 5p2 plus 7p3. And it's less than or equal to that because we're going to choose the maximum. We're going to max P equals V in a second. And so V could be this, or it could be less than, depending on which of the outcomes gets you the most money. Like if they play Y, you might earn more. So V is less than this because we're just going to end up picking the biggest anyway. So V is this one if they play Y, and V is this one if they play Q. And we're going to max, like I said, P equals V. And we're also going to say P1 plus P2 plus P3 is less than or equal to 1. Now, I simply say that needs to equal 1, but just for simplex algorithm to work, you need to add a slack variable in there. And like I was saying before, the table gives you a hint about that. Because when we rearrange all these, we're going to end up with V minus this less than or equal to 0. So we'll add in a slack variable to make that equal to 0. And likewise, add another slack here, another one here, and another one here, because otherwise you don't end up with enough slacks to fill in this table here. So we're going to add in slacks to all of them, and then put all of our slacks there, and pull all of our ones across here. So V, P1, P2, P3, and then all of the slacks, like so. And now we can just fill in all of the coefficients that we see here. So this first row is going to go 1, -5, -7, 1, and then all these will be 0 because they all go away. Or there should also be a 0 here because the P1 is not there. And then equals 0. And then likewise for the other rows. Second row is this one because the S2 comes from there. Third row is this one because the S3 is there. And then the S4 from there, so that's going to be this one here. And then likewise this one here is the last one to do. Okay, they usually ask a question like this, and it's basically the same thing. So it's just doing that every time. Now, the problem has been solved. So they solved all this table here using simplex. That's fine. Good thing that we have to do that. And P1 is that. P2 is this. So, of course, P3, just assuming that the slack variable is 0, we can say P3 is this. Of course, it just has to be. And now we can work out the value of these V's using these P's here. We should also we can cross out this row because option R, which will happen with probability P2, is just not happening. So that row goes away. But we can put these values into these V's here and work out these 3 things here. Now, the minimum of these, which is equally these 2, is the value of the game. And that's what player B is going to aim for because, of course, player B is losing this amount every time. So they're going to want to lose the least amount every time they can. So let's just say player B plays X at Q1, Y at Q2, and Z at Q3. We would want, therefore, these 2 things. Sorry, no, we don't. Not these 2 things. If we're playing, if the other person is playing option Q, then we have our winnings will be this row added together, and we want that to equal this. And likewise, if the other person is playing option S, then we'll have this row with the Q1, Q2, Q3 equaling this. And of course, the other equation that we're going to get is because all three of those need to equal 1. And now we can just solve these in the calculator maybe and get those three Q values. Now, once you've got those Q values, that's the strategy for player B, right? That's just what you say they do. Now, the other thing that you could have said there to make it a bit easier for yourself was, like I said, B is aiming for this to happen here, not this. So, but this came from this row here when B played Z. So basically from that, we should learn that B shouldn't play Z. Also, look at this row and this row here. Z is just dominated from B's point of view by Y. B loses more, because remember, this is how much A gains every time. B loses more by playing Z here than they do Y, and here than they do playing Y. So they just shouldn't be playing Z. So we could just say that B plays it at 0 and just have two probabilities instead. And then we do the same thing, matching it with the value of the game, which are these two. And you don't even need the third equation, of course, and you end up with these two as well. And that will be the other way to get that question done. Anyway, thanks for watching, and I'll see you next time.